Okay, let us start our session. Good morning, dear colleagues and guests. Let me declare open a session of the Dissertation Council for the Defense of Thesis by Korolev Sergei for the degree of Candidate of Physics and Mathematics, Specialty 010405 Optics, on the theme Multipartite Entangled State of Light for One-Way Quantum Computation. By the order of St. Petersburg University, dated the 7th of July 2020, 6498/1, me, Sokolov Alexander Ivanovich, Doctor of Physics and Mathematics, Professor of the Department of Quantum Mechanics of St. Petersburg University, was appointed Chairman of the Dissertation Council. Other members of the Dissertation Council were appointed by the same order, and let me introduce them to you. Marshak Igor Cheslavich, Doctor of Physics and Mathematics, Professor of the Department of General Physics of St. Petersburg University. Kazakov Andrei Alexander Yakovlevich, Doctor of Physics and Mathematics, Professor, Head of the Department of Higher Mathematics and Informatics of St. Petersburg State University of Industrial Technologies and Design. In the remote access mode, we have Sokolov Igor Mikhailovich, Doctor of Physics and Mathematics, Professor of the High Engineering Physics School of Peter the Great Polytechnic University of St. Petersburg. Can you hear us? All is well. And Korolkova Natalia Vladimirovna, Professor of the Department of Physics and Astronomy, University of St. Andrews, United Kingdom. Can you hear? Can you see us? Yes, it's a pleasure. Thank you. The degree applicant, Korolev Sergei, is also present. Also, the academic advisor of Sergei Borisovich, Golubeva Tatiana Yurevna, Doctor of Physics and Mathematics, Professor of the General Physics Department of St. Petersburg University. And at that, this is here I've listed all the attendees. And to improve the quality of communication, please, dear colleagues working in the remote access mode, switch off your microphones. But remember to switch them on when you're given the floor. Well, let me also inform you that our session is being recorded and broadcast online at St. Petersburg University website, and the speeches are being simultaneously translated from Russian to English or from English into Russian as appropriate. During the broadcast of the Dissertation Council session, an email address is currently displayed to which all the listeners can send their opinions and questions to the applicant regarding his thesis and the ongoing scientific discussion of his speech. These questions shall be forwarded to me by the Technical Support Department, and I shall read them during the discussion. Questions should be related to the applicant's speech and the content of his thesis, and it's mandatory to indicate the name, position, and place of employment of the author of the question. Questions that are not related to the scientific discussion of the thesis, the text in relation to this shall not be read. In accordance with the order of awarding a degree of Candidate of Science and Doctor of Science at St. Petersburg University, approved by the local regulations of the university, a session of the Dissertation Council is considered competent if at least 2/3 of the approved composition of the Dissertation Council, but not less than 4 persons, take part in its work. Our Dissertation Council consists of 5 persons. All 5 members are present, including 2 members of the Council in the remote interactive mode. All the members of the Council and the applicant have audio-visual contact. Thus, we have the quorum, and we may start. Let me set forth the procedure of today's session with the approximate duration of approximately 2 hours. First, the chairman's summary report on the main content of documents submitted by the applicant and their compliance with the applicable regulations. Answers to possible questions, 5 minutes. A brief presentation by the degree applicant outlining the key points of his study. That should take no more than 15 minutes, recommended, or we can give a little bit more time, like 20 minutes. First of all, the applicant may talk in more detail. And secondly, the speeches are being simultaneously translated, so this is hard work. And if we speak too fast, that will be the translator's job will become even more difficult. So I suggest we give 20 minutes to the degree applicant. Questions to the applicant strictly on his report, no more than 2 minutes per question. Answers of the applicant, maximum 5 minutes for all the questions. 5. Speeches of all members of the Dissertation Council in turn with their opinions, questions and suggestions to the applicant. A summary of their suggestions to the applicant, no more than 10 minutes for each speaker. Speech of the chairman and his review, approximately 10 minutes. Answers of the applicant to questions and remarks of members of the Dissertation Council, that should not take more than 20 minutes. 8. Open discussion. Speeches at the request of those present at the defense with a summary of their positions and or with specific questions and suggestions to the degree applicant strictly on the theme of the study, no more than 2 minutes for each speaker. And that all the interested persons are kindly requested to register in the registration sheet and to fully introduce themselves before speaking. 9. Presentation by the chairman of questions to the applicant sent during the discussion, in the scientific discussion, the broadcast at the Dissertation Council session. Final answers, no more than 2 minutes. 11. Speech of the applicant's academic advisor, maximum 3 minutes. 12. Discussion by members of the Dissertation Council before the open voting of the results of the defense, during which the broadcast sound shall be switched off, approximately 5 minutes. 13. Open individual voting, and the chairman of the council should count the votes and the results should be recorded in the minutes of the meeting. Decision on awarding or not awarding the academic degree to the applicant, and finally closing remarks of the applicant, no more than 2 minutes. Dear colleagues, do you have any questions or objections to this procedure? If there are no objections, let's start implementing the procedure, but please remember to switch off your mobile phones. Thank you for your attention and thank you for your understanding. Let me start the session. Chairman summary report. The thesis by Korolev Sergei for the degree of candidate of Physics and Mathematics, Academic Specialty 010405 Optics, on the theme Multipartite Entangled State of Light for One-Way Quantum Computation, was accepted for defense by order of Academic Secretary of St. Petersburg University on the 6th of July 2020, order number 6455/1. Korolev Sergei wrote his thesis at St. Petersburg University under the guidance of Doctor of Physics and Mathematics, Professor of the General Physics Department of St. Petersburg University, Golubeva Tatiana Yurievna. The number of publications which outline the key results of his research, according to the enclosed list, is 6. In peer-reviewed scientific publications are released approved by Ministry of Education, 0 publications. Journals indexed in the Scientific Database of Weight of Sciences Corpus, 7 publications. The applicant submitted to the Academic Secretary of St. Petersburg University a full package of documents for acceptance for consideration and defense of the thesis. All documents correspond to Article 12 of Section 3 of the Order. All the documents submitted by the applicant, according to the information I received from the curator, comply with the requirements and are kept in the applicant's attestation file. Copies are available with the officer of the Dissertation Council Activity Support Department, who is now present at the session. So before I give the floor to the degree applicant, do you, dear members of the Dissertation Council, have any questions to the applicant? Is it necessary to read and disclose the full list of documents submitted? I see there are no questions. Then, Sergei Borisovich, the floor is yours. You have 20 minutes. Good morning, dear council members, dear guests. Today, let me introduce my thesis on multipartite entangled state of light for one-way quantum computation, written at Physics faculty of St. Petersburg University, Department of General Physics, undergraduate of Golubeva Tatiana Yurievna. Before we talk about quantum computing, let's look at why they are needed in principle and what advantage the quantum computer should provide. First of all, let us talk about the problem that classical and quantum computers can solve. In computer science theory, all problems are divided into several complexity classes. Here's a diagram of some of them. The first and the simplest class is indicated in diagram as P class. Problems of this class can be solved on the classical computer at a time that depends polynomial on the size of the input data. This class includes, for example, integer addition, division. The second class is an exponential class, which is denoted exp in the diagram. The problem contained in this class will be solved by a classical computer in a time that depends exponentially on the input data. For example, the problem of factorization of a number, problem of Modal of quantum systems, so on. Problems that can be solved by a quantum computer belong to the so-called BQP class. Problems that belong to this class include finding prime dividers of numbers, finding solutions to equations, simulating quantum mechanical systems, etc. Moreover, the boundary of this class is related only to algorithms. That means that creating a prototype of a quantum will open up solutions to problems that are not available today. Also, it's necessary to say that the borders of this class are related only to quantum algorithm that are currently known, and is this knowledge, these borders will broaden. Currently, there are many models of computing. In my paper, I investigate a one-way modal calculations of continuous variables. Such calculations are performing local measurements of multiparticle entangled states. These states are the main source for performing these calculations. In this framework, we had several goals. First, to analyze the process of generating cluster states of various configurations, so understand which cluster systems we can generate with a limited resource. Secondly, we need to find out which cluster systems we need suitable for universal quantum transformations. And third, find the optimal strategy for conducting quantum calculations which guarantees the smallest errors. Let us proceed to next slide. Here I have summarized literature and the main cluster state. As cluster state is a partly entangled state that can be characterized by a graph. In this nodes of this graph of physical systems is entanglement between them. And this graph of cluster state can be weighted, so each can correspond to a particular number, and generation of quantum oscillators are used. It is important that each oscillator should be compressed. And for certainty, we assume that they all pass by Y quadrature. Mathematically, a cluster state can be defined using a set of its nullifier operators. Shown here in this slide, these operators on cluster state by acting on it. This nullifier can be recorded in a adjacent matrix or cluster state graph. The adjacency matrix is by the definition of I, eta, and iota, is responsible for the link between the nodes. Once we have defined the cluster state, we can define the process of calculations. The whole process can be divided into several stages. In the first stage, we generate a cluster state. After that, we make so we should want to transform. At the same stage, we choose nodes that will not be measured in the future. At the next stage, we make local measurements are performed. At that, the states are destroyed, but since this state is connected with other subsystems, measurement of one state affects the other subsystem. And as we perform the measurements, we arrive to unmeasured nodes, which will be in the output state some quantum transformations. So the main purpose of one-way unidirectional calculations is to implement universal quantum transformation. A goal of all quantum calculations. For universal quantum transformation, it's necessary to perform two operations, Gaussian and non-Gaussian operations. By definition, Gaussian transformations, Hamiltonians, all are non-Gaussian are all other operations. It's necessary to perform three types of operations. First type is quadrature rotation, second compression operation, and a two-mode operation. For example, we have considered the CZ operation. I want to emphasize here that the main purpose of my work was to study Gaussian operations. The matter is that non-Gaussian operations have already been theoretically demonstrated on a two-node cluster state, and such states are minimal, which means, as will be obvious from chapter 3 of the thesis, they are optimal for non-Gaussian transformations. Let's proceed to the main content of my thesis. Let me start with the generation, cluster state generation. As already mentioned, first stage of compressed oscillators. To do this with Boголюбов, those oscillators transformed from independent to cluster state. In my work, I managed theoretically analyze this transition and define a universal expression for Boголюбов transformation. It's shown here. A is an adjacent matrix of generated cluster state, which corresponds to cluster state, and Q is a free or orthogonal matrix. Also, I managed to record a formula describing nullifiers of cluster state with compressed quadrature vector. Using this expression, I formulated following if have same compression and are independent, the mean quadrature can be performed for a mean quadrature of compressed oscillators in the following form. In this expression, it's important that there is a relation only on coefficients of cluster states, on configuration of clusters, and here there's no dependency on Q, the method of generation of cluster states. Using the result of the theorem together with the separability criterion, we formulated two consequences. The first consequence is recorded here. It provides criteria of quantum oscillator compression necessary for cluster to generate cluster of a specific configuration. So when we know which configuration we want to generate, we may answer the question which compression is needed. And the second consequence is explains which generation we can generate having oscillators with particular compression. With these two consequences, I have formulated two provisions. The first provision, a simple tool for the possibility of constructing non-separable cluster on available fixed compression resource and the explicit type of cluster configuration has been obtained. If clusters we need is of given configuration, and how to calculate the maximum compression. After we have formulated this condition on physical systems that can be used for cluster generation, we may proceed to study one-way computations. The process is divided into several stages. This slide describes these stages. Here, let us focus on stage 2, where we add input states to cluster states modes. At that state we create nodes that will not be measured, And here, two cases are possible. In the first case, when input nodes are added to output nodes, unmeasured. And secondly, we mix it with measured values. Let's look at the first case, when input modes are mixed with output modes. Having theoretically analyzed this scheme, I was able to describe the relation between input and output quadratures. The formula is bulky, but it's analytical, and it can be used to answer the question which transformation can be realized in this computation scheme. So this scheme is two-mode transformations similar to CZ, but have a different, an additional transformation of compression. Unfortunately, single-mode transformations cannot be realized. Is not realized in this system, and so there's no. We may not call this scheme universal. Let's look at a different situation when input states are with clusters, and in this case, the number of nodes does not exceed the two-node transformation. In this, we input and look even more frightening. But then again, they haven't analyzed it. We may say that two-mode transformation in this scheme can be realized very well with fewer errors. A universal single mode cannot be implemented in this scheme. If we try single mode transformation, we get such a general, we see factoring of the main rotation, compression, and another rotation. If angles, the rotation matrix were independent, then we could talk that transformation is universal. But in this case, it's not. This is not the case. We see only a transformation which is close to universal. Let's remember this result because we're going to use it need it in the future. And to a single mode transformation, we increase the number of nodes and consider the case when the input modes the number exceeds twice the number of input modes. In this case, the general expression can be written, and there are 5 schemes of 4 node cluster states which can be realized. It's important that 4 nodes in clusters is a minimal number necessary for implementation of single mode transformations. Why is necessary to find the because we need adding such oscillator into the system, and increases the number of errors proportional to compression. So the more oscillators we have, the more errors there are. This result enables us to formulate 2 more provisions. Provision 3, we identify 5 can be single mode, both other cluster configuration that meet universality did not exist. We proved that if the number of nodes exceeds twice the number of input modes, computations can be universal. Well, now we know which configurations are appropriate for implementing universal single mode transformation. So now we can optimize the computing process. By optimal process, we mean process with smallest error. And to discuss errors, let's see what errors depend on. This slide shows an equation which links input and output quadratures of computing with cluster states. Here we may see that the main transformation depends on 2 factors: cluster state configuration, weight coefficients, and the computation method. The second member is responsible for error, depends on configuration and on the computation method, and Q method is responsible for generation. Yet, if we proceed from operator values to mean quadrature fluctuations, because that's how errors are evaluated. The relation with Q matrix disappears, and then error depends only on configuration. This enabled us to make one more provision. The transformation and the computation error depend only on cluster state configuration and not on the method of its generation. Using this equation, we may evaluate the transformation error, as was shown earlier. That's how the vector looks, and that's how the error vector of single mode transformation looks. Even though we have 5 different schemes of realization of single mode error, these schemes coincide. And now let's try to minimize errors, which we just got. For this purpose, let's go beyond the standard one-way computations model, by measuring single mode transformations. Here we have reviewed schemes, and both schemes are based on the fact that on 2-node scheme, single mode transformations can be realized. So first case we used 2-mode cluster states, and in this case the computation error looks as follows. In the second case, where we used 2-node cluster state complemented with linear optical transformation, which is quadrature rotation. In this case, single mode universal transformations. Comparing all the 3 schemes of universal single mode transformation, we can see that in this scheme we get the smallest error. And if we compare these 2 schemes, it's easier to compare them from error vectors to the norms. Here the norm of these vectors, and orange is of this scheme. We may see that in some points, some transformations, this scheme implements computations better. Now let's talk about optimization of 2-mode transformation CZ. In the thesis, we look at 2 schemes, additional schemes. One scheme looks as follows. It implements CZ transformation and error set by this vector. The other scheme is shown here. Here, for implementation of the CZ transformation, we use calculation on 2-mode cluster state as a phase rotator, and recorded as follows. Comparing 3 schemes, we may see that in this case we get the smallest error. This enabled us to put forward another provision saying that minimal error of in using 2-mode cluster states together with additional as phase rotator. This slide shows my a list of my main publications on this theme, and here's a list of events where the results were presented, and all the provisions put forward for defense are summarized here. Thank you so much for your attention. Thank you, Sergei Borisovich. Next, the applicant must answer questions. Do we have any questions at this point? Natalia Vladimirovna has a question. Natalia Vladimirovna, please. I have a question about regarding slide number 7. And you identified a very interesting relation. Thank you for your interesting presentation. You found that you can calculate how many nodes are needed. Please tell me. is not only node number, but configuration is also important. With the help of this formula, can you measure only the number of nodes or configuration as well? Thank you for this question. You see, this formula determines the number of nodes and also provides evaluation of the maximum node, the maximum number of nodes at specific compression. For example, if we have in this system several differently compressed quantum oscillators, using this formula we may see if oscillator is compressed to the maximum, the number of neighbors of this oscillator can be this, and if it is less compressed, the number of neighbors would be this. So, and then we can assess the possible configuration, but in general, on exact configuration, we cannot answer. So the only thing we can know is the number of neighbors. Thank you very much. I see. More questions regarding the presentation? I have a question, please. My question is, I did not understand. You discuss cluster states, a number of nodes in a cluster. Is it always smaller than 4 or 5, or for any number you're working with any number? So all the expressions we obtained for any number of nodes in cluster state, but since every new node adds error to the computation scheme, so our aim was to find the minimal number of nodes for computing, which requires the minimum number of nodes. So all the results we obtained with the minimum number of nodes, not to increase error. I have another question. Can you hear me? My question is, in your thesis and in your presentation, you mentioned that hybrid computing schemes have an advantage, as you said in the final part of your presentation. Please tell us, have you analyzed how smaller requirements to compression get, and can your theorem be adjusted to this case? I see. Thank you for this question. The hybrid schemes shown here are needed to minimize the number of nodes in a cluster state, which bring errors into computations. And so, using this minimum number of nodes, we put in the minimum error in computations. So we also considered losses that may occur in these linear optical elements, and we found that these losses are minimal, and as a result this hybrid scheme yields better errors than the scheme with only with a cluster state, where computations are based only on the cluster state. Thank you. More questions? Do we have more questions? Council members, do you have more questions? here is my question. Please turn the microphone on. Please introduce yourself. Sokolov Ivan Vladimirovich, professor of General Physics Department 1 of St. Petersburg University. What methods of input state have you considered? Because entangling, impact, optical entanglement, maybe something else, your general schemes are connected to the method of joining the input objects. Yes, in our work we looked at light divider method, so we assumed that this is the optimal transformation. They are very common and implement with it implements very well. May I ask another question? Yes, of course. You said that at some stage the result does not depend on preparation of the cluster state, depends only on its structure. What does that mean? What does this independent means with this, given this structure? Have a look. To transform oscillators from compressed state to cluster state, we have Bogolubov transformation written here. It's a free orthogonal matrix responsible for its free and knows an infinite number of transformations that transform one oscillators into cluster state of a particular configuration of adjacency matrix. And when we perform computations, mean error fluctuations do not depend on the method of cluster state generation anymore. They depend on the number of nodes, on their location, on entanglement, but not on preparation of a cluster state of a particular configuration. Thank you. There's another question. There are no more questions. Natalia Vladimirovna has a question. I have a question. It's very similar to Ivan Vladimirovich's question. Why should we expect? I cannot. The state where this. So why you expected it to be dependent? Thank you for this question. When we consider cases of computations where all oscillators are equally compressed, there is no difference in preparation of the cluster state. But if we look at cases with oscillators with different compression, here the generation scheme is relevant, and by changing the scheme we can minimize errors somehow. But about that I'm going to talk later when answering questions. Thank you. Thank you. More questions? At that, let's finish our preliminary discussion and let us proceed to the next item. Speeches of the Dissertation Council members with reviews. And according to the procedure, first I have to read the external review sent by professor of Moscow University, Korolev Sergei Pavlovich, and it's a short review, so I'll just read it. So the review on thesis by Korolev Sergei Borisovich, you know the theme and the specialty. Thesis of Sergei is dedicated to impact of various configurations of cluster states on one-way quantum computation cluster states, one resource for computations of this type. That is why this study is significant from fundamental and practical point. Relevance of the work is explained that the growing interest to creating quantum computing on various physical platforms. Such device, in theory, can solve a number of fundamental applied tasks, for which a classical computer would spend much more time. The first significant result of the thesis is identifying criteria linking configuration cluster state with compression of quantum oscillators used for generation of this state. According to this criteria, cluster states with the smallest number of connections less demanding to physical resources to compression of quantum oscillators used for their generation. In other words, the author has demonstrated that for compilation is advisable to use clusters with fewer number of connections. On the basis of theoretical study, the author identified the connection between configuration of cluster states and type of transformation potentially implemented on them. From the practical point, the greatest interest is results of search of such configuration of such cluster states optimized for realization of one-way computations. The author has demonstrated that free quantum Gauss transformation is best realized through computations on two-node cluster states, which is a linear optical device as a phase rotator. Such transformation method leads to smallest errors in the results. In addition to that, two-node cluster states contain only one connection between two physical systems, and that means they can be generated easily and are less demanded to compression of the used quantum oscillators. Thus, the thesis by Sergei Korolev on the theme Multipartite incandescent light for one-way quantum computations by its relevance, high level of performed research, novelty of results, and scientific and practical corresponds to the main requirements set by the order of the 1st of September 2016, number 6821/1 on the order of awarding academic degrees at St. Petersburg University. And the degree applicant Korolev Sergei Borisovich deserves being awarded a degree of candidate of physics and mathematics, specialty 010405 optics. Doctor of Physics and Mathematics, Professor of the Quantum Electronics of Faculty of Physics of Lomonosov University, Head of Quantum Technology Center, Kulik Sergei Pavlovich. The review was written on the 3rd of August this year. And next, in this review, there are no critical remarks. So nothing to answer. You don't have to answer to react to this review. Now let us hear the reviews of the council members who read the thesis and submitted their reviews. First, I'd like to give the floor to Mashek Igor Shislavich. Dear council members, dear colleagues, I will not read the descriptive part of my review and will proceed straight. The thesis made a very favorable impression on me. The author has worked hard, obtained new and useful results which have theoretical and practical significance. The author developed tools can you use for quantum computations of physical resource, identified optimal strategy for such computations. By not questions but critical remarks, I'd like to say the following. For use single-way computation with the use of free system evolution. However, the author does not take into account errors caused by this procedure. How reasonable is this? And in conclusion, I have to make the standard conclusion. The thesis by Sergei Borisovich Korolev on multipartite incandescent state of light for one-way quantum computations corresponds to the main requirements set by the above-mentioned order, and the degree applicant certainly deserves being awarded a degree of candidate of physics and mathematics, specialty 010405 optics. That's all. I'm done. Thank you. I suggest that you answer questions right away. Thank you for your question. Indeed, additional universal transformation CZ, we considered this scheme where additional rotation of quadratures is necessary by quadrature rotation to implement a universal single mode transformation. If we perform such a turn with the help of free evolution, do nothing, and oscillators will turn. But this method will result in many errors. That is why in our work and in experiments we used rotation with the linear phase elements such as phase rotator. This method implements with much less error this transformation. So if we compare the errors, quadrature rotation error is 2 orders smaller than quadrature offset error. So therefore we ignore this error. Thank you. Thank you. Next, I'd like to give the floor to Alexander Yakovlevich Kazakov. Good morning, dear colleagues. I will not read the positive part of my review and the descriptive part. I would like to say that I was pleasantly impressed by the thesis, and the results seem significant to me, and in this line which I have been watching, for line of work which I have been watching for many years, I think we are making good progress. So I'll just read my questions. In the beginning, in the introduction, it says that the methods will be based on the use of multipartite entangled states on quantum variables. So it will be interesting to see in the thesis the comparison between discrete quantum variables, and this I never found this. The text discusses the possibilities of so-called nullifiers for fixation of cluster states, and I never saw how the requirements to the set of nullifiers for determination of cluster states. And my third comment: it seems to me there is a lack of detailed discussion of criteria of separability of cluster states. In particular, it's not quite clear how one can take into account the randomness of choosing canonical variables. When we discuss separability, then there is, it looks like something is missing. It seemed to me that you needed to discuss in more detail how it is possible you use some separability criterion which appears incomplete to me. Otherwise, the thesis made a good impression on me, and I think that the degree applicant deserves to be awarded the degree. Thank you. Your answers, please. Thank you for your questions. As for your first question, indeed, such a comparison would be appropriate, more detailed comparison of these variables, but due to the limitations on the length, I had to complete only discrete and continuous variables in 2 aspects. error correction procedure, and implementation of this comparison is given on pages 15 to 29. As for your second question about nullifiers, I'm sorry, I was not able to sufficiently highlight this in the text, but nullifier of cluster state shown in this slide. It's an operator set in the following way: the y quadrature of y quadrature of cluster neighbors with its own coefficient set by the graph of the cluster state. So this operator is a nullifier of a cluster state, and for the state to be cluster, it's necessary that these nullifiers influence in the state to bring it to zero. As mean cluster state should tend to zero, must tend to zero, and then we may say that the state we are observing is a cluster state. As for your third question about separability criteria, here I shown the general formula of separability criteria. Van Luca is true about all canonical variables, shown here x, y. If there is some freedom in choice of canonical variables, this randomness is taken into account in these coefficients h, k. They change somehow for them, for some variables, and change of those coefficients will be reflected in the right part. So when choosing different canonical variables, the right part will change. So the number will change, which tells us that they have separability state, non-canonical variables, and we may say that we have a measurement result smaller than a given number, and if we change the variables on the right, the constant will change, and the criterion separating separable from non-separable state will also change. So that's my answer. You know, for here you have h and g. These are parameters that we are using. For some h and g, we need to achieve this for some. For example, if we look at cluster states, the cluster state, and our aim is to measure the cluster state, then we choose this h and g so that they turn to nullifier of cluster state for some y, which is hk, and as a result let me show you. Here we get one nullifier and another nullifier, and on the right we get a criterion by which these two nullifiers are members, and we can is this entangled or non-entangled state. Using h and k, we may say that if it's entangled or non-entangled. So still remains a mystery to me, because when we discuss entanglement, we need all the possible variants, not in one single, but for all have to describe. But maybe this is my personal thing. So are you satisfied with the answer? Next, let me give the floor to Natalia Vladimirovna Korolkova. Natalia Vladimirovna, please present your review. Dear colleagues, I will not repeat the positive part of my review, though I would like to mention that I think this is an excellent work. I was very impressed by the results, and for creating particular cluster configuration, what resources are needed, and what can be created with these resources. So this is the work is very timely, very fundamental, has great practical value. The use the excellent results. From the point of speaking of questions, I have 3 main questions. I shall read them quickly. You have already discussed in your presentation. There's a difference between oscillators. So please, could you please say how optimal is the choice of similar oscillators? What do we get by changing if we use different oscillators? I think to answer this question, you need a separate study, but from your experience, it will be interesting to learn. So this is one question. A second question: you said it is impossible to consider Gaussian transformations. Is impossible, can be fully universal if we work only within Gaussian transformations. That is why this result is unexpected. My question is, you selected to reduce error, but you demonstrated it's impossible to make the transformation universal. Have you considered the other methods to achieve universality? And finally, or maybe a comment or as personal curiosity, maybe your scheme with the addition of linear elements to quantum computations using by additional mechanism. And formally, I have to say that, of course, the degree applicant deserves to be awarded the degree of candidate of physics and mathematics. This is an excellent work. Thank you. Thank you very much for your questions. I'd like to say that Igor Mikhailovich Sokolov had similar questions, so I will try to answer 2 questions at the same time. Indeed, if we consider differently compressed oscillators, then criterion will change. For example, in this slide I have shown, let's assume all the oscillators are set by this expression, this equation, where P is some constant, positive constant, and this average mean root oscillation fluctuation, and in this case the evaluation the minimum compression criteria for cluster state shall be recorded as this. And unlike in a case we have similarly compressed oscillators, here we have 2 new members. These 2 new members are positive, and so in a general case they reduce this value. They will reduce this value. That means that the requirement for compression increases. So we need more compressed oscillators. Easier to understand this on an example. Let's look at a 3-node cluster state. If oscillators, if we use similarly compressed oscillators for generation of this cluster state, it's necessary to 0.96. If we consider oscillators with different compression, then we get this picture: maximum compression is minus 0.24. So if we have similarly compressed oscillators, they all similarly compressed, and if we increase the compression, the other oscillator, we need to release to preserve the entanglement in this scheme. So, and this is exactly what we can observe here. The oscillators here became less compressed. Speaking of evaluation, what is optimum? What is the optimal case when the two oscillators are equally compressed? It's easier to understand this using an example. For example, we want to generate a very complex cluster state. In this case, for example, we have some physical source generating optimal compression, maximum compression. And in this case, if we have equally compressed, we can generate a cluster state. Compression will be sufficient to generate this cluster state, but if we increase one node, we have to release, and we cannot do that because our source cannot generate more compressed oscillators, and that means that using equally compressed oscillators is better. But this is the case when we need complex state. If we need to generate simple states on computation process, on process of generation of cluster states, this will have no impact. Also, I'd like to say that previous question, the scheme may influence. If we have equally compressed oscillators, there's no relation on Q matrix. When we have oscillators with different compression, you see Q matrix appears here that will remain. So methods of cluster state generation will have a serious impact on the scheme. For example, we can more compressed oscillator we should put in the center, so the number of nodes will be bigger, and by changing the scheme we can optimize our computations. Here is a link to a paper which explores synchronized parametric oscillator. They have a source with specific compression, and they are exploring these variations in the scheme to achieve the minimum, the smallest error. As for what else it impacts, calculation, it has impact on the calculation error. Here the compression is the same, so the error, if the error in oscillators, then the error will get another member. Let's look at this example. As we may see, in this case, the error is smaller than in that case. That means, so what happens when we have a less compressed oscillator? They have a greater impact on the error. So as less compressed oscillators have the bigger oscillators, they bring greater errors. So and that generally makes the error bigger. As for your second question, which also coincides, it's quite similar. So I will try to answer both questions. As for implementation of non-Gaussian transformations, in my work the main purpose was to find the optimal strategy for implementation of one-way quantum computations, one-way computations cluster with minimal number of nodes, because every new node increases the error. And unfortunately for us, implementation of non-Gaussian transformations, cubic phase transformations, has been demonstrated on two-phase cluster state with the minimum number of nodes. And in this here, I have shown this generation scheme. There's a two-node cluster state which shifts. Then we measure number of particles of the cluster state, and we get the so-called cubic phase transformation. Then we use the state. With the help of this scheme, we can transform this transformation into the input state, and thus we can implement non-Gaussian operation. Unfortunately, other schemes which suit better I could not find. And regarding your third question about similarity, some similarity between scheme with the phase rotators, with a scheme with additional. Yes, I think there is certain similarity, because in the method of error minimization, in our case we minimize errors because cluster state can be used with the minimum number of nodes, 2 nodes, and such cluster state can be used because we use this phase rotator. This phase rotator is also adjusted to the results, to measurement results, homogeneous results we conducted, and adjusted to the implemented transformations that we want to perform. So choosing this rotator, we implement transformation with the smallest error, and using a scheme with one additional, it also has contains errors, the measurement results obtained at earlier stages that affect the measurement method of this additional indicator. So the results are adjusted, so we may also somehow perform the transformation with the smallest number of errors. That's all. Natalia Vladimirovna, are you satisfied? Yes, I'm generally satisfied. I have only one small comment I have in question 2. You look only this cubic phase transition to, but then there is another method to take non-Gaussian measurements, partial measurements of photons. So maybe in the future it is reasonable to look at this, to consider this possibility also, but I am satisfied with your answers in principle. Thank you. That's all. Yes, that was a good suggestion. Thank you. Next expert is Sokolov Igor Mikhailovich. The floor is yours. Dear colleagues, first of all, I'd like to apologize. As for the thesis, I really liked it. It gives whole number of interesting, significant theoretical and practical results. I'd like to emphasize too that Natalia Vladimirovna already mentioned this defining connection between cluster configuration, and secondly is prediction of error for hybrid schemes with one-way computations. And I'm sure the results will have good practical application. As for the critical remarks, I am lucky in a way. Two of my comments were very similar to comments made by Natalia Vladimirovna, and I already got answers, and I thank the applicant. As for my remaining this second chapter shows that unweighted cluster state is less demanding, the final degree of comparison. And in conclusion, you say that question of influence of weighing coefficients of cluster states remains open. So I have a question. What are the reasons to believe that the use of weaker compressed states in a cluster may be appropriate? So this is my question. It has no impact on the overall positive opinion of this work, and I believe that Sergei Borisovich certainly deserves to be awarded the degree of candidate of physics and mathematics. Thank you. Sergei Borisovich, thank you for this question. Indeed, it was demonstrated that generation is better with unweighted cluster states, less demanding. Let's assume we have well-compressed oscillators that can generate unweighted cluster states and weighted cluster states. And in my opinion, the question of which cluster states should be generated is still open. The expression which shows the results of computations looks as follows. We may see that the first member responsible for the main transformation depends on the weight coefficients, and the computing error depends on the weight coefficients. So if we generate a cluster state with different weighing coefficients different from 1, then already at the generation state we may include some transformation in the result and vary the computing error. Let's look at an example on a 3-node cluster state with weighing coefficient 1, 2, 3. When we can get this transformation, rotation transformation and compression transformation. That way, we see that compression depends on the relation between the weighing coefficients, and by changing these coefficients, we obtain greater or smaller compression. And we may also change errors, vary errors. We can reduce this error or that error. It all depends on our tasks. If we need to perform a specific transformation and we have a sufficient physical resource, then we can enter this transformation in the generation scheme and create a cluster aimed at additional compression of input quadratures. So it seems to me that the question of using weight coefficients is still remains open because of that. So that's what I think. Thank you. Are you satisfied with the answer? Yes. I didn't like the expression varying errors. I'm sorry, I missed. I'm sorry, I did not hear. Could you please say the word? I didn't like the phrase to vary errors. Errors should be reduced. Yes, yeah, I agree. Yes, to reduce. The aim is to reduce errors. Yeah. Okay, accepted. Yes. Thank you. And the last review is mine. I liked this work very much, not because of its content, but by the very fact that it exists. I am very pleased that at our university scientists are working in this sphere I shall not read the standard part, the description of the advantages, and gives summary of the content. So I shall just read the final part of my review. Speaking of the thesis in general, I should mention there's a complex study of one-way quantum complications in physical systems described of continuous variables. The material has been tested. There's 7 publications in leading specialized magazines and discussed at numerous international seminars, conferences, and schools. And as for advantages, I have not found any serious drawbacks. The minor defects is strange facts in the literature list. Not only original articles published in Russian magazine of quantum electronics, spectros, but their English translations. This is a funny circumstance, which is symptomatic. We are losing our capacity to speak Russian, but this is just a minor comment. And as for, I have only one comment. The author analyzes errors of one-way calculations on four-mode clusters and comes to the conclusion that for some transformations, the probability of errors sharply increases. It would be appropriate to indicate what these transformations are and whether the superiority of calculations is preserved with an abnormal increase in the number of errors. Otherwise, apart from that, I really like the work, and I think it corresponds to all the main requirements applied, and the author deserves to be awarded the degree. Welcome. Thank you for your question. Indeed, when calculating a four-node cluster, we have a situation where an error for some transformation increases. So, but what are these transformations? Transformation of a quadrature expansion and compression, expansions and expansions of some input quadratures, and at the same time extension of errors occurs. But since we are using compressed oscillators, existing errors, even those extended errors are still much smaller than the main transformation, and because they are much smaller, they can be adjusted by error correction codes, which means quantum superiority, and errors do not take computing from the quantum category. Thank you very much. We finished our discussion. Now I have to ask a general question. Dear members, is everybody satisfied with Sergei Borisovich's answers? Silence. No. Please, maybe someone else who is not a member of the Dissertation Council would like to give his opinion. Nobody seems to be willing. No one is willing to speak. Then after that, I have to read the question sent by email. Let me read the question. The question was sent. My name is Tikhonov Kirill Sergeyevich. I am Associate Professor of General Physics Department of St. Petersburg University. What is the minimal degree of compression of input oscillators at that cluster state is prepared for implementation of error-resistant one-way computations with a large number of logical operations with kind regards Kirill Tikhonov. The answer to this question goes beyond the scope of my thesis. We are currently working on this, and so I have an answer. Before, when we assumed that for implementation of universal Gaussian transformations, we need to use 4-node cluster states. The was 20 and a half dB to implement transformations that were completely error resistant, where errors will not increase and affect computations. But in our case, when we use this scheme with 2-node cluster state, complemented with a phase rotator, we managed to improve this result, and we obtained approximately 19 dB, sufficient to implement universal Gaussian transformations. Okay. Since this question was sent by email, 19, I have a question, 19 dB, and what can you implement 15 and a half? In reality, universal quantum computer unfortunately cannot be implemented because of these compression issues, but here I'm talking about the universal, but we can implement quantum co-computers that can implement some operations needed for specific applications with some error, and if the number of errors is limited, then we can reduce the needed compression. Thank you. If no one is willing to speak, I'd like to give the floor to academic advisor of Sergei Borisovich, Tatiana Yurievna. The floor is yours. Thank you, dear colleagues. I am very pleased. I was very pleased to listen to Sergei, and I must say this is our group's success to see a student like that graduate, because Sergei found himself in a very difficult situation. He was a pioneer in our group when we started working on one-way computations. That is why I must say that he performed enormous work, and he dealt with numerous issues, some well-known he had to master and explain to us, and in that sense he has worked very hard. His work was enormous. Speaking of Sergei's task, his task is natural because these clusters can have different configurations, and what configurations should be used. When we found that same computations can be performed on different configurations, cluster configurations, we needed to optimize them, and Sergei studied this issue, and in my opinion he gave a very complete answer to this question from the point of Gaussian transformation, and his work is very interesting, very useful, so I'm very pleased with his work. Thank you. Next point is specific. Since some council members are working in the remote access mode, and because of that I have to ask if council members and others present and the degree applicant have any unanswered questions related to working in the remote access mode. If you have any questions, please let me know. If you have any comments or remarks, all is going well. No claims, no critical remarks. Now I have a question to the council for the council members. Now we have the opportunity before we vote to take a break to discuss the result, to have a private discussion, small private discussion of the dissertation council. Do we need to do this? or everything is clear. My opinion is that the situation is very clear, very transparent, so we don't need this private discussion. And then let us proceed to voting. At that, I have to ask council members in the remote access mode if you can see and hear me, because I'm going to ask some critical questions now. I put the question of awarding to Korolev Sergei the degree of candidate of physics and mathematics, specialty 010405 optics, and to open individual vote. And I have to ask personally each council member. Igor Chislavich, your opinion? I am for. Alexander Yakovlevich, I am also for. Igor Mikhailovich, I am for. Natalia Vladimirovna, I am for. Thank you. I am also for. Thus, on the basis of 4 council members voted for, no one voted against, and no one abstained. The decision to award to Korolev Sergei Borisovich the degree of candidate of physics and mathematics, specialty 010405 optics, has been made. Dear colleagues, again I have to ask you a formal question, since our session is some members are working in the remote access mode. Do council members or the degree applicant have any comments regarding the procedure, regarding the voting procedure? This is a formal question. I think no one has any remarks. And one of the final points is the closing remarks of the degree applicant. Thank you very much. I'd like to thank all the council members for taking part in the session. Many thanks to Tatiana Yurievna Golubeva for her assistance with writing my thesis, the positive attitude, and big thanks to all members of the Quantum Optics Laboratory and General Physics Department for good discussions of various issues, and thank you to my family for their support, their great support. Thank you. Very well. Then, on behalf of our Dissertation Council, let me congratulate Sergei Borisovich on being awarded the degree. And at that, I declare this morning's session closed. Thank you, everybody.